we've got one more emergent property of water to go. Talked about the cohesive properties, the high specific heat, or the moderation of temperature regarding the specific heat, then the vaporization, etc., the insulation of water by ice, and now the fact that water is a universal solvent, or not universal, is a really great solvent, called the solvent of life even. So let's talk about solutions really quickly. A solution is a liquid that's a homogeneous mixture of substances. So basically, it's entirely mixed throughout. So if you were to take a sample from the top, sample from the bottom, you would get the same concentrations of everything in it. And there's a couple parts of the solution. Solvent is what does the dissolving. So say you're making chocolate milk, milk is the solvent. Then you will be dissolving the solute in the milk, in this case the chocolate. So whatever is being dissolved is the solute. And then an aqueous solution is one in which water is the solvent. So say, for example, I'm making lemonade, water is the solvent, lemonade powder is the solute, whereas in the chocolate milk example, not an aqueous solution because milk is the solvent, but lemonade is an aqueous solution. Water is a super versatile solvent due to its polarity, which allows it to form hydrogen bonds really easily. So it's basically going to form hydrogen bonds with whatever you're dissolving in it, if whatever you're dissolving is polar. Nothing is a better solvent than water, but water still doesn't dissolve everything, which is good, because if it did, it would dissolve your cells, it would dissolve this glass, it would dissolve your house when it rained. So it's a good thing that water doesn't dissolve everything. So when we are dissolving an ionic compound in water, it's because of the polarity of water that it dissolves. So let's look at this picture. So right here we have NaCl, which you should know is table salt. So if you were to take a spoonful of salt, dump it into a thing of water, the salt is going to dissolve entirely. And that is because this salt is just made up of sodiums that are stuck to chlorines because of their full charges. Sodium is fully positive, chlorine is fully negative. But then water, when we dump it in water, now the polarity comes into play. So remember that the oxygen end of the water molecules are a little bit more negative than the hydrogen end of the water molecules. So there's just these little tiny charges. The little tiny charges still attracted to the big charges. So basically, this chlorine is going to get entirely surrounded by water molecules. And the hydrogen ends are all going to be attracted to the negative chlorine because the hydrogen ends are a little bit positive. You see in this picture, all the hydrogen ends are stuck around the chlorine. Opposite with the sodium. Sodium is positive, so the negative oxygens are attracted to it. When an ionic compound is dissolved in water, each ion gets completely surrounded by a sphere of water molecules. This is called a hydration shell. So this right here is the hydration shell around chlorine, hydration shell around sodium. So this is flat because your computer screen is two-dimensional, but it would be completely coated. So let's say that nothing around me I can use. Say I'm holding a chlorine ion in the middle, there's going to be water molecules all around it. That's the hydration shell. And because of this, that's why salt gets completely dissolved, because we just spread out sodium and chlorine ions in between all the different waters. And anything that's ionic or polar is going to dissolve in water for this specific reason. Because of the partial charges on the water molecule, it goes and breaks everything up. And then you have dissolved your solution. So then there's water can also dissolve compounds made of non-ionic polar molecules. So I already said that. So it can be completely ionic like salt, or it can be just a polar solution like proteins dissolve in water because they're polar. Even large polar molecules such as proteins can dissolve in water if they have ionic and polar regions. So any kind of molecule that has a charge on the outside can be dissolved in water. So here's a protein. You can see that proteins have slight partial negatives and partial positives, so they are polar like water. So water just comes in and dissolves. You can see the hydration shell around this protein molecule completely covered in water molecules because of hydrogen bonding. So then we have these things called hydrophobic and hydrophilic. I'm sure you could guess what these mean. Hydrophobic is a substance that loves water. Philic means love, so it's drawn to water. Whereas hydrophobic is afraid of water. You know what a phobia is. Hydrophobic compounds don't like water. So oil molecules are hydrophobic because they're nonpolar. There's no partial charges, so water isn't attracted to it, doesn't care, and it's not attracted to the water. They're indifferent to each other. So the water molecules are all going to stick together, which means that the hydrophobic solution is going to be by itself because the water molecules are all sticking together and not sticking to it. And then a colloid is a stable suspension of fine particles in a liquid. So this is when you have something that isn't going to dissolve. Could be polar, it's going to be polar, but it's not getting dissolved for whatever reason. And so it's not mixed in, it's not a solution, just suspended in the water, and it's what a colloid is. Okay, so, for example, cotton is polar but does not dissolve in water. So water molecules stick to the cellulose that cotton's made out of. Cotton is made from a plant, the molecule is cellulose. So water molecules stick to cellulose but don't dissolve cellulose, which is why if you have a cotton towel, it absorbs water but it doesn't dissolve. So it's really helpful for you because then you get to dry yourself off when you get out of the pool, but your towel doesn't dissolve because it's polar. The water sticks to it, but it's not dissolving. Sorry. So your book says biological chemistry is wet chemistry. So any chemistry that's happening in regards to life has to do with water, which is what we talked about. Water is super important. So molecular mass is the sum of all masses of all atoms in a molecule. So water is made up of two hydrogens and one oxygen, and the molecular mass of water is 8. Don't quote me on that. Something around that, like that. Sum of all the masses in there. I'm sorry, 16. Duh. No, I don't know what it is. But the number of molecules is generally measured not in molecular mass, but in moles. So 1 mole is 6.02 times 10 to the 23rd number of molecules. So we call this Avogadro's number. There was a guy named Avogadro who came up with this. And that's what a mole is. 6.02 times 10 to the 23rd. You should know that from chemistry. And then molarity, capital M, not little m meters, capital M is how we measure concentration. How we can tell, basically, how chocolate is your chocolate milk? Did you put in 1 scoopful of chocolate or 5 scoopfuls of chocolate? And we would measure this by, it's the number of moles of solvent of solute per liter of solution. So something is pretty weak, it's not very concentrated, it's going to have a really low molarity. And if something's really, really concentrated, you put in like 10 scoops of chocolate, because there's a lot more chocolate in there, it's going to have a much higher molarity. So that's how we talk about the 4 emergent properties of water. Again, they are cohesion, moderation of temperature, insular properties of ice, and solvent of life. So those are very important. And they're all because of hydrogen bonding of water. Very, very important.